Hello, everybody. Thank you for coming. This is so exciting to be kicking off a two-day conference on satellite data for energy analysis and policy. To our knowledge, this is the first ever large-scale conference connecting satellite technology and insights with energy decision-making in the private, public, and nonprofit sectors. So we're really thrilled to have all of you here. And for folks who are watching online, once it's posted, hope you enjoy as well. So we have 2 great days planned, and I'll be telling you a little bit more to kind of orient us. But there's really no better way to kick us off than to have a few words from Dr. Steve Ackerman. Steve is our Vice Chancellor for Research and Graduate Education here at the university. And what that means is that he is in charge of all research and all that we're on. But Steve's own background has been built up as a leader in satellite data applications, especially in the field of weather. So he really brings a deep knowledge to the topic that we are talking about today. And within the OVC GRE, RGE, actually that is the home of both of the Wisconsin Energy Institute and the Space Science and Engineering Center. So even within the big picture framework that he's working on, it kind of has a point of connection for these 2 broad fields that have so much in common, as we will learn over the next few days, but that maybe haven't been brought together as closely as they could be moving forward. So Steve, thank you for joining us.
Thank you, Tracy. I'm very glad to be here. As Tracy said, I'm the Vice Chancellor for Research and Graduate Education. And I want to point out that coupling, that we look at research and graduate education as explicitly linked. I'll try not to move my hands as much there. And that's one of the things I really like about this EAP program, is that they look at those linkages. They consider the scientific, the technical, the economic, the social concerns that all feed into developing energy policy and decision-making. And so for those graduate students in their program, I think you're going to get a great research. And for those of you who aren't in it, you should get in it, because that coupling between graduate education, research, and the broad aspect that EAP brings to the program is wonderful. Again, on behalf of campus, I want to welcome all you visitors. This is a perfect place to have this kind of conference, because Wisconsin is the birthplace of weather satellites. It all began here. So welcome, have a great meeting. I would love to stay, but unfortunately a meeting came up and I got to go to a meeting I don't really want to go to. All right, thanks. Good luck.
Thank you. And if Steve's voice sounded familiar to those of you here in Madison, he's one of the weather guys on Wisconsin Public Radio and also writes a regular column for the Wisconsin State Journal. So yeah, so it's really, really nice to have you here, Steve. Thank you. So Steve mentioned the EAP program, which is the host of this event, and that is the Energy Analysis and Policy program. It's a graduate certificate program open to master's and PhD students across the university, and it's been here since 1980, making it one of the oldest graduate energy programs in the United States, or really the world. And actually, this conference originally was going to be the 40th anniversary of the EAP program in 2020. But something happened in 2020. Of course, the world shut down and we canceled the conference, delayed it. And in 2021, we still weren't sure. And so this is really special here in 2022 to be coming together for an event that's been a very long time in planning. But as we came together 2 years after the 40th anniversary, we wanted to do something that captured the big picture, cross-cutting nature of our graduate program and the faculty and students involved in it, while really launching us on a new trajectory ahead. And one of the reasons satellite data came to mind is in part because over the years, we've met with industry leaders, including Ben Seda from BP, who's here, and who've mentioned like that the satellite work going on here at campus is very interesting to the energy industry. And to me, that was very eye-opening because, you know, we all wear a lot of different hats. And one of the hats that I wear is chairing our EAP program. And I was actually hired here in 2003 as part of an initiative on energy. But I have a different hat where I lead the national team for NASA, trying to make satellite data more relevant to public health and air quality. And I've been leading that team for NASA. We call it HACAST, for the Health and Air Quality Applied Sciences team, for about 10 years, both as the deputy director and now the director. And we have meetings every 6 months where we bring together stakeholders like the EPA and the state of California and the American Lung Association to learn and talk about what satellites can do, what they can't do, and help chart a path forward. But there's really never been anything like that for energy. So here we are. And this would not have been made possible without the support of a wide range of sponsors who I want to make sure to recognize, because they really have been fundamental both to the intellectual shape of the conference as well as to providing these nice venues and events. And that includes NASA, Alliant Energy, Madison Gas and Electric, the Space Science and Engineering Center, led by our co-chair Brad Pierce, BP, Energy Transitions, Renew Wisconsin, Clear Spring Energy Advisors, the Nelson Institute, the Wisconsin Energy Institute, the Office of Sustainability, and a special thanks to Martha Goodell, who is one of our alums and hosted the kickoff reception last night for speakers, sponsors, and alums. By way of a few sort of cruise director comments to kick us off, I wanted to note that we have a number of events lined up for Friday afternoon, tomorrow afternoon, following the sessions that are taking place today and tomorrow. Sign-ups for these events are right outside the door and include a tour of the Space Science and Engineering Center, a tour of the Wisconsin Energy Institute, a career panel for students with Alliant Energy, a training session on how to use a NASA data platform led by Paul Stackhouse at NASA Langley to make satellite data more relevant to energy advisors, and a online talk from Duke University by one of our colleagues who couldn't be here with us today. There's also today, of course, a great lineup of sessions. Usually they are, you have a choice between option A and option B, where one option will be in this room and one I believe is in the Northwoods room. We have coffee breaks where we hope you will meet people you don't already know and work with. And we then have a reception later tonight, a movie night tonight by one of our own faculty, Paul Wilson, who's going to be showing some of the 2022 Netflix documentary, Meltdown 3 Mile Island, and talking about it from a perspective of nuclear safety and policy, which is really going to be exciting. Even my 13-year-old is coming in to hear that. And then tomorrow morning, we have more great talks, and then the afternoon of events that you can sign up for. So that's sort of where we are in our intellectual and practical launch of this meeting. And now I'm going to introduce to you the chair of our kickoff panel, Max Duckworth, and he will lead it from there. But before I hand it over to Max, I just want to make sure to thank a few key people who've been involved in the planning of this. There are co-chairs Brad Pierce and Morgan Edwards. And with Brad coming from the satellite side and Morgan coming from the energy policy side, we really have a great partnership there. Paul Stackhouse at NASA Langley has played a major part in the planning, and none of the logistics would have been possible without Maria Vices from Space Science and Engineering and SIMS, who I believe is outside giving name tags, Jenny Bratbert, and my team here who are working on the NASA Health and Air Quality Applied Sciences team, and really all of you, because this would not have taken shape without your engagement and attendance. So to launch us, I want to give a little background on Max Duckworth, who will be carrying us forward. Max is an impact investor and advisor to early stage mission-driven companies. He co-founded MaSa Partners, an impact investment venture, in 2015, and has since made 24 investments in startups disrupting and delivering real-world solutions in energy and climate, natural resources, food and ag, and other fields of innovation. Max spent 14 years at Constellation Energy in Baltimore, Maryland, where he held a number of commercial executive leadership positions, including global head of trading and co-head of commodities. He led large M&A transactions, including a $5 billion divestiture of Constellation's nuclear units to the Environmental Defense Fund that resulted in the creation of the Constellation Energy. Is that the right EDF or a different one?
Electricité de France.
Oh my gosh.
So as not to impugn that.
Oh yes, yeah. Well, I thought about that. Like, why would they be buying all these nuclear facilities? That makes no sense.
They are carbon free.
Well, there you go. Okay, this is why we bring industry and academics together, so we can correct some of these things. That's right. Anyway, Max started his career in energy as a policy analyst, modeling climate, clean air, and renewable energy policies, working with the Department of Energy, EPA, Lawrence Berkeley National Labs, and several other research organizations and NGOs. So I was not totally off base that he works with NGOs. And he's co-authored a dozen peer-reviewed papers that have been widely cited with a bachelor's and master's degree in physics. So really, I think Max's background speaks to the broad scope of this whole conference, pulling together these threads that don't usually go together. And we're so appreciative, Max, of you helping kick us off. So thank you.
Not yet.
Not yet?
Or actually, we can leave it up. That's fine.
Okay.
Good morning. Welcome, everyone. Thank you, Tracy, so much for that kind introduction. And I'd also just like to thank and recognize Tracy, not just for bringing this terrific conference to Madison, but for all of her work and leadership in making the energy analysis and policy program what it is within the University of Wisconsin. I think it's really beginning to develop a national footprint, and we all need to continue to support it so that it can expand. I'd also like to acknowledge our co-chairs, Professors Brad Pierce and Morgan Edwards, and everybody else on Tracy's team who helped to bring this together. So just to start off, when Tracy first mentioned this conference, these kind of thoughts in her mind that were germinating, I was really immediately struck by how timely and topical the conference was. And I think that's even more so the case today. If you just think in the last few weeks and months, you think about record-setting temperatures across the entire Northern Hemisphere. You talk about the devastation wrought by hurricanes Fiona in Puerto Rico and Ian across Florida and the Southeast. And I think, just shifting gears, you also think about the Inflation Reduction Act that was signed into law by President Biden in late August. This is absolutely a game changer. I think at the risk of mixing my metaphors, the Inflation Reduction Act and at least the energy and climate portions of it promise to really pour fuel on the fire of the installation of renewable energy and the adoption of adjacent technologies, not just in the energy sector, on the grid, but also in homes and with respect to mobility. And I was kind of reading an article last night. The Congressional Budget Office expects the whole tax credit and carbon credit part of the IRA to cost $400 billion. But there's a pretty good sign that it's probably going to cost $800 billion. So this is really just a call to action. This is a catalytic opportunity for us to really fast track, everything that we need to do around climate change. So just want to quickly show a couple of slides, which are certainly iconic in my mind, maybe in yours. These definitely were very kind of seminal, at different stages in my energy career. You might recognize this is Hurricane Katrina, going back to 2005. This was a huge event in the energy world because back then this preceded hydraulic fracturing and shale drilling. So nearly all of US production of oil and gas was offshore. And you'll know that Hurricane Katrina just knocked everything over. had a huge impact on the supply side. Now, interestingly, what a difference 15 years makes. Nearly all of our domestic oil and gas production is onshore. So when hurricanes like this kind of emerge in these areas, it's less about the supply side. It's actually more about what they do to the demand side. So just an example of how all of this kind of interplays. Let's see if I can move. Oh, look at that. Excellent. That worked. This is the second slide I really wanted to speak to. And this is obviously a satellite photo of most of the US, I think, at night. And looks very familiar, right? You've got Chicago, the Windy City. You've got the Amtrak corridor. You've got Houston, Atlanta. But when I first saw this photo in the New York Times, I was really struck by a pretty bright area in the top left. Does anybody know what that represents? Because I'm not sure there's a lot of population density and luminosity at night in the Dakotas. Yes. Sorry? Yeah, right. It's the kind of nocturnal flaring of associated gas from oil production, because at the time they still didn't have the gathering systems and the infrastructure to actually store and transport that. So in some sense, I think of the Katrina slide as being the impact of environment on energy. And this slide is really the impact of energy on the environment. So today and tomorrow, I'm really excited to learn more about the interconnectedness between satellites and space, climate and weather, and energy and environment. And certainly, as Tracy mentioned, it's kind of had a profound, all of these themes have had a profound impact on my energy career, whether it's been in my policy modeling days, understanding the impact on greenhouse gas and clean air, from modeling in the electricity sector of conservation and other measures. In my commodity trading days, having to take a view on electricity prices, which are affected, of course, every single hour and day by weather, and occasionally by acute events like hurricanes or polar vortices. And more recently, kind of the hat I'm currently wearing, investing in early stage companies and really trying to accelerate renewable energy technologies and solutions as part of our addressing climate change. So now I get to move on to the fun bit, which is to introduce our distinguished panelists. I will try and make this quick so that I can yield the floor. Apologies, I'm going to read this so I don't get it wrong. So batting leadoff, Professor Brad Pierce on your right. He's the Director of Space Science and Engineering Center and professor within the Atmospheric and Oceanic Sciences Department at the University of Wisconsin. Previously worked as a physical scientist at both NASA and NOAA, and has expertise in using satellite atmospheric composition measurements to improve global and regional air quality forecasting. And then after that, Professor Morgan Edwards, who is an assistant professor of public affairs in the LaFollette School. Her research and teaching focuses mainly on human-centered energy responses to the climate crisis across policymaking scales. And her current projects focus on, among other topics, fixing leaks in natural gas distribution systems, accelerating the phase out of coal power plants, and assessing the equity implications of large-scale use of negative emissions technologies. So a lot of really good stuff there. And then kind of batting cleanup, and I'm really excited about this because not to digress, but as a kid, I really wanted to be in the NASA Mission Control Center when I grew up. And never did I think that I would be serving on a panel, with a distinguished scientist from NASA. And I know that, Brad, you also have a history at NASA. But anyway, so batting lead up is Dr. Paul Stackhouse, who is the senior research scientist at NASA's Langley Research Center in Virginia, with focus areas on climate science and applied science, leading several projects that focus on, among other topics, satellite-based top of atmosphere and surface radiative flux variability and budgets, cloud and aerosol radiative properties and effects of fluxes, meteorological measurement analysis, and I think very importantly, somebody who really brings space to energy, several applied sciences topics, including renewable energy, sustainable building, and agricultural applications. So each panelist will present for up to 15 minutes, and then we'll have time for hopefully a very interactive Q&A session that involves all of you. Thank you very much, Professor Pierce.
Okay, thank you. So the order of these presentations we iterated on a number of times. It's not quite what it is in the agenda. It's going to be me and then Morgan and then Paul. And this session is sort of to set the stage for the rest of the conference, starting with where have we been using satellite data for the last 50 years and its ties to energy, kind of the grand challenge, and then what we're trying to do right now and what we hope to be able to build on based on this workshop. So historical use of satellite data for monitoring and predicting weather. That's where it all kind of started. This is an example of billion-dollar disasters or weather climate disasters last year. It was an unprecedented year with over, I think, 21 different billion-dollar disasters. Each one of these had impacts on the energy system. And so that's the take-home message, is that weather is integrally tied to both our health and well-being, our safety, and our energy system. And how do I advance the slide? There we go. That's fine. I got it. Okay. So as Steve said, Madison, Wisconsin is where weather as observed from space started. This is an image from ATS-1, which is the Applications of Technology satellite. This is when the United States was saying, could we actually use satellites to observe and understand the weather? So think about that. That was, I was 8 years old at this time. And that was when we didn't even think, we had to see whether we could use satellites to look at the weather. This is the first image of the Earth from a geostationary satellite. That means it's a satellite that is in an orbit such that it stays in the same place and rotates with the Earth at the same time. So that it's always looking at, in this case, the Northern Hemisphere. You can barely see in this image on the left-hand side, but that's in the upper right-hand side of that is North America. Here's a zoom in on September 2nd in 1971 from this same satellite showing a hurricane. So that was the first images we had from a satellite to say, can we now use this information to help observe and predict weather? And at this time, I mean, this was truly revolutionary. For the first time, rapidly evolving imaging nearly every hemisphere was possible. We could watch, fascinated, as storm systems developed and moved and were captured in a time series of images. This is what you see on your nightly news every day now. It's become part of our normal life. The spin scan cloud camera on ATS-1 was built here by the first director of the Space Science and Engineering Center, Werner Sumi, and Robert Plant, who was an engineer at the University of Wisconsin-Madison. So this is why we say that University of Wisconsin-Madison is the birthplace of satellite meteorology, because we were the first to help NASA and later NOAA observe the Earth from space. So, but where do we go from there? Here's the first observation of a hurricane out at sea. The track of the hurricane is there. In the past, the Galveston Bay hurricane, no one even knew it was coming. It just hit. Imagine that. Now we're looking at hurricanes evolving weeks ahead of time. Here's what the current constellation looks like. I'm not going into a lot of detail with this, but all those ones on that outer big ring, those are geostationary satellites. They are parked in orbit. They each look at that part of the Earth. That's their real estate. And you can see there's a whole suite of those with both US, European, Russian, Chinese, South Korean, and Japanese satellite. The other thing that's really remarkable about the global Earth observing system, it's a place where international collaboration is a key, because we all have to observe the entire planet. All this data, for the most part, is shared with all these different forecasting agencies as part of a grand observing system. Those ones on those the inner ring, those are polar orbiters. So those are the ones that they're flying around like this. The Earth is rotating underneath them, and as the Earth turns, they're able to observe the Earth typically once or twice per day. And it's this suite of instruments that we use to observe the atmosphere, and then we use those to help constrain our forecasts of global weather systems. I'm going to spend a little bit of time on this slide because it's kind of complicated. This is showing how the evolution of forecast skill, I'm not going to get into the details about how we're defining forecast skill, we can talk about that offline, has evolved since 1981 out to 2017 on the right-hand side of this axis. The blue are 3-day forecasts. So this is how accurate is a 3-day forecast. The red is how accurate is a 5-day forecast, and the green is how accurate is a 7-day forecast. The solid line is for the Northern Hemisphere. The Northern Hemisphere is the hemisphere that has land on it for the most part. And so we have radiosondes, we have surface networks, we have lots of traditional observations that can go into to initialize our forecast system. On the bottom part of these curves is the Southern Hemisphere. The Southern Hemisphere does not have that conventional observing system. And what you see is that over time, first of all, forecast skill improves. I'll get to that. But more importantly, the difference between the forecast skill in the Southern Hemisphere and the Northern Hemisphere goes away. That's entirely because of satellite data. That's the impact of satellite data on our ability to forecast weather. So now that we're observing the whole planet, we're not relying on these traditional radiosondes and ground networks. We're able to have the same skill in the Southern Hemisphere as we do in the Northern Hemisphere. But you'll see that the overall forecast skill grows. It grows in incremental steps over time as we improve our forecasting system and our observing system. Typical skill, valuable skill, is about 60%. 50% means you flip a coin, half time right, half time wrong. And what you can see is now, as we get to about 2003 or so, we now have skill at 7 days. So that's a real accomplishment. That says that now emergency management, energy industry can start using forecasts to start making decisions out to 7 days. And that's a pretty critical point. I'll get back to this 10-day one where we don't have predictability at a little bit later point. So I'm going to spend a little bit of time on a case study that's all very familiar to us because it was very recent, Hurricane Ian. This is a 5-day forecast of the track of Hurricane Ian from the United States Global Forecast System. And it was spot on in terms of its track. Okay, we still have uncertainty and we have improvements to make in intensity. Hurricane Ian did a rapid intensification right before it reached the shore with 150-mile-an-hour winds when it went on shore. But in terms of track, we're able to do a very good job of predicting this. That means that all the emergency management teams and the local government agencies and industry can help. They can respond ahead of time before landfall. That's a major accomplishment that didn't exist before. So this is a loop that hopefully will play. There we go. This is image from the geostationary satellites, our new ones. It's looking in the infrared. So what we're looking basically is at cloud top temperature, but here's the eye of the hurricane as it hits Fort Myers. And we're now able to look at this this is now the visible image. This is what you would see if you were at the International Space Station. And you can see actually structure within the eye of that hurricane. The spatial resolution, the temporal resolution of our current geostationary satellites is unprecedented. And we're able to see this like we've never seen it before. Go on. Okay. So what do we do with that data? Here is another example for Hurricane Ian. This is from poweroutage.us. It's showing customers without power just after landfall on September 30th. And you can see 60 to 100% of the people in the Fort Myers area were without power. As Max showed an iconic slide, we can use now the VIIRS day-night band. That's the visible infrared imaging radiometer suite. That's on one of our polar orbiters. It goes over once a day, once a night. And we're able to actually look at September 26th, the Fort Myers area and the city lights before the hurricane, and September 30th, where you can see these dramatic reductions in lights and indicating major power disruption in this area. You can see up in Port Charlotte as well. So we're able to use these new data sets to look in real time at some of these energy impacts. So now I want to go switch gears a little bit in terms, instead of talking about hazardous weather and disasters, I want to talk a little bit about long range forecasts. And this is really forecasting chaos. That 7-day limit of predictability, that's sort of predicted by Edward Lorenz in chaos theory. That's about the limit of prediction of a deterministic kind of model. And to predict beyond that, you have to start doing ensemble type forecasting systems. So this is illustrated here. So this is how we tackle that sub-seasonal to seasonal kind of forecasting system. We have an initial condition, that's that analysis at the far right of this figure on the left, and it has some uncertainty. We reduce that uncertainty in the initial conditions by adding more observations, but there's still uncertainty. That uncertainty grows with time, and so a particular forecast has very little skill. An ensemble of forecasts, we can start aggregating them, and it's been shown that that ensemble of forecasts has skill. So that's the idea behind these ensemble forecasts. To tackle that 7-day or 10-day and beyond, we go with that. And that's where you see the information that particularly the energy organizations use is these NOAA 30 to 90-day climate predictions. We're not predicting landfall of a particular hurricane or the temperature at a particular place, but the probability of being warmer or colder. So these sort of temperature outlooks and precipitation outlooks become a really important part of that kind of 30 to 90-day planning within the energy sector as a whole. Same thing holds true for drought. This is the current drought monitor showing the unprecedented drought that we're experiencing in the Western US. And here's a prediction of the tendency of that drought. With the next 90 days, as you can see, much of the country will continue to be in a drought. That again has a huge impact on the energy sector. So this is kind of just a quick snapshot of that. We'll be talking more about that in the future. If we look on the upper left, there's where biofuel resources are in the energy sector, obviously impacted by drought. If we look at the upper right, this is where all the different power plants are. Hydroelectric certainly is going to be impacted by drought, but so will all the thermodynamic, the steam generating power plants. So coal, gas, oil, nuclear are all going to be impacted by drought because they need water to generate electricity. This is just a Lake Powell, Glen Canyon Dam, picture of that. And we're actually now reaching an unprecedented level, a level that wasn't present at the Lake Powell Dam since it was filled. And so that's kind of where we are in terms of that Western drought in the US. So to kind of close out, just a summary slide, and this sort of transitions into Morgan's challenges that she will be discussing. So we already have significant impacts of extreme weather and climate change on the energy system. These are some just examples from all the things that we'll be talking about today. And I just want to close with saying that satellite data will continue to play a critical role in constraining the predictions of extreme weather events and the long-term probabilistic forecast. And that's what we're here to discuss today. Thank you very much.
Okay. All right. Hi, everyone. It's great to be here. I'm Morgan Edwards. I'm an assistant professor of climate policy, and I'm just so excited to have everyone here together in this room to talk about what I think is such an exciting and emerging topic, both for satellite data and for energy. I'm also excited to be following up on Brad Pierce's comments because what he talked about was really a success story of satellite data informing decision-making on a really important and energy relevant topic. And so what I'm going to talk a little bit about in the next few minutes is some of the grand challenges that I see coming up for the energy sector in the coming decades, and the ways that we can build on these earlier successes of using satellite data in decision applications to think about a broader suite of decisions that we need to be making in the energy system. So as you'll see, some of these applications, like weather prediction, are already very well developed. Others are kind of new and emerging. So we'll walk through what some of those look like. But before we talk about the challenges in the energy sector, we can't talk about those without talking about climate change. So the climate crisis is really a challenge multiplier for the energy system. The world has already warmed by over 1 degree Celsius. And of course, we're concerned about that, not just because of the warming, but because all of the extreme weather events that Brad was talking about. So wildfires, floods, droughts, hurricanes, all of these have huge impacts on the energy system. And that means from a policy and planning perspective, we really have these two fundamental challenges. The first is to dramatically reduce emissions from our energy sector. So energy is responsible for around 70% of greenhouse gas emissions. So we can't tackle the climate crisis without thinking about our energy system. But we also need to adapt to the changes that are now at this point already baked in. So think about how can we make sure that our energy delivery is reliable in the face of kind of growing changes in our climate. At the same time, we're seeing growing concern about climate change here in the US and also abroad. So I from a policy perspective, I like to say that I think actually the public is much less polarized on this issue than sometimes our politicians can be. We actually see a broad recognition now. So 76% of the US population, this is according to the latest Yale climate opinion surveys, think that climate change is happening. And for the first time in their latest survey, over half of the population now, 55%, think that people in the United States are being harmed now. And so what that means is that we're seeing a surge of mobilization and calls to action for climate policy. And climate action will mean big changes for the energy sector. So these are kind of the three big pillars that we need to address to reduce emissions here in the US, but these extend elsewhere as well. And all three of these have tight ties to energy. So the first is kind of accelerating towards 100% clean electricity. This means phasing out high emitting fossil fuels and rapidly scaling up renewable energy technologies and other low carbon technologies. The second is decarbonizing our end uses, so reducing emissions from our buildings, industry, transportation. This is primarily through electrification and efficiency, but also through low carbon fuels. And then finally, a little bit less directly tied to energy, but still with significant links, is thinking about enhancing our ecosystems. So enhancing the carbon storage potential of forests, of farmland, of coastal wetlands. And the main takeaway is that satellite data can support decision-making on each of these three pillars. And I'll talk through a couple of examples of ways that satellite data is already doing that and can do that in the future. Another big trend, and this is true particularly in the US, but again across the world, is that we're increasingly seeing that climate action is taking an all-in approach. What that means is that we're not just looking at nations, countries making pledges to reduce emissions, but we're seeing all kinds of different actors involved in climate action. And so this map shows, this is before the 2020 presidential election, subnational actors in the United States who had made commitments to uphold the goals of the Paris Agreement. So this means limiting global temperature change to 1.5 degrees or well below 2 degrees. They've made commitments to do that. So that includes us here in Wisconsin. And so even before we had the more recent surge in federal action on climate change, these actors were already globally significant. So they represented 71% of the US GDP, 68% of population, and over half of total emissions. And this is important because many of these different actors, as they start thinking about ways to reduce emissions, many of these have implications for the energy sector. They'll have very different data needs and capacities to use different types of data products. And so when we start thinking about the role that satellite data can play in informing these real and very urgent decisions, we need to think about the kinds of tools, the kind of resources that not just national governments, but the private sector, city governments, states will need to inform these decisions that they're making. And we're also now recently seeing a surge of climate action at the national level in the United States. And of course, the big pillar of that Max kind of foreshadows is the Inflation Reduction Act. So the IRA has a big focus on energy and climate change. It's primarily carrots rather than sticks. So what that means is lots of investment. So tax credits for manufacturing clean energy technologies and expanding production. It means incentives for solar, wind, and then like personal technology, so electric vehicles, building efficiency, heat pumps, kind of unprecedented levels of investment in these new technologies. There are some other important elements that I'll highlight because they relate to some of the panels that are going to be coming up later. A methane fee, and then also changes in fossil fuel leasing on federal lands that have more kind of mixed impacts in terms of emissions. So after the IRA was passed, and even before, I do a lot of energy and climate modeling. A lot of the modeling shops all across the US were trying to ask the question of what could this all add up to? So this graph shows results from the Rhodium group, but different groups kind of all came to very similar conclusions that IRA could reduce emissions by around 40% by 2030 relative to 2005 levels. And so the best expectations before IRA were that emissions might be reduced by around 30%. 50 to 52% is the US Paris Agreement target. So that means that IRA has kind of gotten us halfway there to meeting that target. So it's a big, big step, and there's still a lot to do. Most of these emissions reductions are coming from the energy sector, the biggest source being electric power. And that makes sense because as we think about these other end uses and the ways that we reduce emissions in those sectors, primarily through electrification, we need low carbon electricity to make that a climate beneficial proposition. But we're also seeing, estimates suggest that there will be direct reductions from industry, direct reductions from transportation. We're also seeing growing investments in carbon removal. This is both kind of technologies to suck CO2 out of the air, like direct air capture. This is also all kinds of land management practices that, again, satellite data has already played and can continue to play a role in tracking and thinking about those commitments. True to its name, IRA is also expected to lower household energy bills. So estimates are putting the annual reduction in energy bills for an average household by 2030 at potentially over $100 per year. So helping through efficiency, through adoption of new technologies, to also significantly reduce energy costs. But there's a lot more to do, and I'll highlight a couple of pieces that I think will be relevant for some of the panels that will come up later on. And that's things like continuing building energy efficiency, new building codes, and also massive investments in electric power transmission. So things that we know that we'll need to kind of meet the scale of these challenges. And so I'll just spend a few minutes talking about, as we think about these challenges, these are really ambitious commitments, and now we're starting to see really ambitious dollars put behind these commitments. But all policy is implementation, and so there are still a lot of questions about what will actually happen in practice. And so how can satellite data support us in meeting some of these energy policy and planning goals? So as we were trying to answer this question and kind of looking around in the literature, what we saw is there are lots of individual communities who are thinking about how satellite data can play a role in different types of problems that have relevance to energy. But nobody had sort of brought that all together and thought about what can we learn from these different communities. And so that's what I led a review paper with a number of co-authors. Some of them are in this room. We also have this conference here. And part of the goal is for us to think about how can we all learn from each other, from private sector, from researchers, from nonprofits, government, and think about how satellite data can support us across these different energy policy and planning challenges. And so I'll just highlight a few of those challenges that I think will come up in a number of the panels that we'll talk about today and tomorrow. The first big challenge is scaling up clean energy. So I already talked about this earlier, the massive scale up that we need to meet our climate targets, but arguably this scale up is unprecedented for the energy sector. Even if we look at kind of other periods of rapid expansion of electricity infrastructure, thinking about like the rapid expansion of gas plants, for example, what we need to see for solar and wind to meet these challenges, even greater levels of growth. And so that means that we have all kinds of new data needs or enhanced data needs, estimating energy resource potential, siting and finding building windows for installing clean energy technologies. This can be particularly important as we think about scaling up offshore wind. And then critically important, forecasting intermittent generation. So this is already a challenge and something that we're thinking about in managing our electric grid as we move to a grid that's increasingly dominated by intermittent energy technologies. These forecasting challenges will be even more acute. Obviously, weather prediction plays a big role in this forecasting. It's not only weather, but it can also be pollution. So things like smog events that can affect the ability of our solar panels to produce electricity. A second big challenge is meeting energy demand. So even as we want to reduce emissions from our energy sector, we also across the world and still in this country have large areas of unmet energy demand. And that takes different forms in different locations. One of the big trends that we're seeing globally is a trend towards kind of massive growth of cities. So this is an example, images of New Delhi in 1989 and then 2018, showing this rapid urban growth. And this growth means new kinds of energy challenges that are even more compounded than they were before. This is an area where satellite data has been a historic strength. So Brad mentioned the kind of lights at night, kind of using those as a way to estimate electricity and energy use across the world. And there are many recent advances, thinking about uncovering multiple and changing dynamics of energy poverty and access. So moving beyond, it's not just asking the question of whether the lights are on or off, thinking about reliability of access, and thinking about kind of predicting forward, looking at these rapidly expanding cities that are changing the dynamics of who is experiencing lack of electricity access, where it was maybe previously thought of as more of a rural challenge. We're now seeing rapidly expanding cities and peri-urban settlements where meeting electricity demand is an emerging challenge. Another big area is predicting energy demand. One key way to do that is by observing changes in urban forms. We can learn a lot about how much energy we use from what our infrastructure looks like. And that we can use satellite data to do that not only in 2 dimensions, but now new research is kind of thinking about how can we look at urban upgrowth as well. So densification of our urban environment. And then we also expect to have large changes in energy demand due to climate change. So being better able to predict demand for heating and cooling, which is again, deeply tied to weather prediction. A third key challenge is reducing energy impact. So obviously reducing greenhouse gas emissions is a key challenge, but the energy system has many, many other impacts on the environment. And so Tracy mentioned that tracking health relevant pollutants from energy systems is in some ways a success story of the use of satellite data and integrating with decision-making. And key challenges in this area will be using satellite data to evaluate compliance with regulations, and importantly, kind of developing increasingly high resolution pictures of how air pollution is distributed across space, and using that as a way to kind of interrogate and identify inequities in the impacts of our energy system. So this is a picture showing Baltimore and Washington, DC. But a lot of recent research has been using satellite data and other data sources to our energy system. These impacts aren't just in the air, though. There's large impacts of energy systems on land and water. 1 minute, got it. And this is an area where in some ways, there's been a historic strength in kind of using satellite data to evaluate compliance with deforestation policies, monitor corporate commissions or emissions commitments to emissions reductions, and an area that we can continue to expand, especially as we think about, Brad gave the example of water cooling. And then the fourth and final area is responding to disasters. So this image here just shows San Juan before and then 2 months after Hurricane Maria, and you can see the kind of continued lack of electrification or electricity access in parts of the city. But we're thinking about with disasters, things like oil spills, gas pipeline leaks. So being able to track disasters over time, tracking wildfires, but also identify disasters before they occur. So monitor our electricity transmission infrastructure, looking for risks of ignition. And then finally, supporting disaster response and recovery. And so I'll just end with a few common themes that I think Paul will pick up on in talking about some satellite data uses. One is a need for high spatial and temporal resolution and long time series to track impacts over time. This is something, particularly in the temporal dimension, that satellite data has a lot of advantages, and increasingly we're seeing more and more high resolution results from satellites that can help us also interrogate some of these spatial questions. Fast response time, especially for a resource prediction and disaster response, so more quickly getting the data in the hands of people who are making decisions. And then finally, accessibility to a large number of stakeholders. So figuring out how to make sure that this data is usable and accessible, that people know about it for utilities, local governments, companies, and communities. So I'll stop there and pass it off to some examples. That's a slow projector. Oh, 1 second. You can advance with this next button.
All right. Thank you very much, Morgan and Brad. This is just a great chance to get together at a really, seminal place for satellite technology. And I'll be noting that as we continue here. But our theme here is, okay, we have a big challenge. We have all these data from different platforms, a variety of people using them in different ways. But can we make this usage even more pervasive? How do we get this information? First of all, we have to define what information is needed out there. And so we'll talk a little bit about that. So, but then how do we put it in, the hands of the engineers, the architects, the managers of buildings and alternate renewable energy systems and clean energy systems? How do we get it to the people that are making these design decisions? And then from there, communities and policies governing towns and cities and urban and large regions. So it's a big challenge. And so what we have here is a project that aims to do just that from the data products that we have been developing and improving within NASA, and particularly at the Langley Research Center. But we have a project here, we call it POWER, but it's aimed at providing Earth observations with a focus of 3 different themes. There's actually a whole applied science within NASA, and energy is just a new emphasis. But we've been doing this, we're talking about historical perspectives. We first got asked to provide information on how much sunlight hits the surface of the Earth in the late 1990s, because we had a project doing that. And we had a group wanting to put refrigeration in Africa, and they didn't have any information. They went to the National Renewable Energy Lab and they focused on the United States, and they sent us over to MaSa. And that's where we started. And from there, we have developed the capability to provide data products specifically in formats in ways that folks can use them. So here's three examples. Renewable energy development. This is Wicked Joe's here is a coffee roastery in Maine. Put in a solar wall, save $40,000. I'm sorry, $10,000 for you at 40,000 square foot facility, and they saved $10,000 per year in Maine with their cooling costs. And then we have the 3M company, and we'll talk about how they're using the data products, but they're actually using the data products. So is the University of Michigan to manage all their facilities, and we'll show you how that happens. And then we've actually had impact because we feature solar irradiance to the agricultural industries. Okay. So let me see here. Trying to advance. Jenny, you said the down arrow goes. Oh, there it goes. Okay. So we mentioned at first Max mentioned radiation budget. Well, what is radiation budget? Well, it's looking at the exchange of sunlight into the Earth atmosphere and the thermal infrared emission. So if more sunlight comes in than emission goes out, you have heating. And that's actually what we're seeing here. But to do this, we've strung together years of, oops, jumped ahead there. Years of, that's actually supposed to spin up there. I'm not sure why. Years of imagery. So Brad showed you the geosynchronous array of satellites all around the world. Starting in 1983, international collaboration put together a long time series of all those imagers. And we've used that to estimate the top of the atmosphere radiation budget, but also the surface. And that's where the historical data starts. But through the years, we've also have this mission called CERES, which is the Clouds and Earth Radiant Energy System. Actually, CERES was based upon an older instrument called the Earth Radiation Budget. And the first Earth Radiation Budget was developed by Vern Sumey. So it shows you the little the expansion through time. So, but these projects process all the Earth's clouds data, and then they observe that energy exchange at the top of the atmosphere. But because we have all the cloud data and we have all the information about the atmosphere that we need to compute the irradiance at the surface, and we have information about aerosols and gases, we have to put all that, fuse all that together to estimate the amount of solar irradiance. But then we also have all these other parameters. So this was all aimed towards science. The question is, can we provide it to folks for applications? How can we help society? And then another aspect Brad mentioned, let's see here. Another aspect is providing, so from space, you can't observe surface temperature, but you can observe parameters similar to it, or you can take observations from the surface, from the balloons, from satellite information, and you can assimilate it into a model. And you can use those observations to optimize the model output. And so this is done at Goddard Space Flight Center's Global Modeling and Analysis. And what this movie shows is how assimilation essentially works. So through time steps, they're integrating these observations from geosynchronous satellites, from polar orbiting satellites, and those go into optimizing the model output. And so they'll have a complete global information system producing surface temperatures and humidities and estimates of winds and all the other parameters that are needed. So we use the observations of clouds And then we supplement with all the measurements, the estimates from these model runs to provide a complete set of information to make decisions. Now, the challenge is to put those decisions into people's hands. So how do we do that? Well, the Power Project, we have a web tool, and was already mentioned, we have a demo of that tool. If you're interested, we can show you how to pull down the data, interact with the data. But we've developed many ways to pull those data down. Of course, we're still improving those. The key is this application programming interface, this API service. Most of the NASA data products have been available historically in these very obtuse formats. They make it very difficult for the public to pull the data. But we've been able to process the data, change the units for the particular industries, and then put it out through this API, this basically URL command. But we also provide this data access viewer. This data access viewer actually uses the API, but it allows the user to interact with the data to drill down and get the specific parameters and information for the dates that they need. And we go all the way back to the early 1980s. And then we're developing these web services as well. So are people actually using it? Well, this figure here gives you just a glimpse of who is using our data access viewer. And the point of this is to show the relationship between where the user is physically and where their projects are. And the point is with global long-term data, we're enabling projects from anywhere sitting in one part of the world to anywhere in the world. Okay, so this is a big thing. So you can see actually we've introduced some GIS compatibility, and we've had almost 200, probably over 240 million requests since 2018, but 560,000 different users. And you'll notice that there's white dots. Each of these white dots shows where data was requested for. Some of these are in the middle of the ocean. So we're providing global data. So we actually do provide the oceans as well. And we have companies like, maybe you've heard of Saildrone, this new company that's has drones that float in the ocean, take measurements. They're able to use the data products that we're providing at this point. So yes, people are using the data all over the world. Another way to use the data, Morgan mentioned spatial, temporal resolution. We have long time series, which are very good for interannual variability and variability in general, but we're relatively coarse resolution. But you can infuse that data with other data products. This is an example just for a student project for the city of Satellite Beach, Florida. And they said, well, if we had PV on all the roofs, how much energy would we get? And so they're able to take our data products that gives general solar irradiance, some information on tilt, and they were able to use that information together with LiDAR analysis of the roofs in their area, fusing that information together to make that estimate. This city council liked it so much, they decided that this was just a student project, but they employed a true consultant to change the policy in their city. And then another thing that we do, which is very critical for enabling all that usage, is to partner with those who develop specific decision support tools. One of those is RetScreen International. This is by CanMet Canada, Natural Resources Canada. And their tool not only is useful for citing of feasibility studies. So for instance, they work with the World Bank. They do feasibility studies for new projects, all sorts of clean energy projects. And then you can make a feasibility proposal and try to get some funding. So that's one of the aspects. But so they use the historical data, long-term averages. But another application is they do monitoring. So they actually can do models of building that depend on the variations of the weather, the solar, the wind, the temperatures, the humidities, and how the use of the building, the way it's designed, the occupant, how many people are in it, and what is it, a lab, is it a data center, the type of building it is, and you can do a building model. So it's critical. They have 750,000 worldwide users. NASA Langley has using that tool. And so but not just for a building, but for all the buildings in the center. And so here we have the orange lines are the prediction of the envelope of different buildings on NASA Langley Center. And the blue lines are the verification, the actual usage. So you can see the model works quite well and replicates the seasonal cycle. And then we had a furlough and everybody left. And so now, based upon the weather, you get the model that predicts what would have happened if the furlough never happened. And then what is the difference in energy that was used, because you still have to keep the buildings on. So now is the difference of that occupation. I was trying to get something from COVID, but they didn't quite have it done yet. So, but it gives you a sense of the cost of the energy and the occupancy and the different models there. And then also we've worked with ASHRAE, which is the American, it's now incorporated, but it stood for the American Society for Heating, Refrigeration, and Air Conditioning Engineers. And historically, they developed climate zones, maps of climate zones, and only from surface observations and only for the United States. Morgan mentioned building codes. Well, all your building codes depend on what your climate zone is. Okay, so ASHRAE determines your climate zone. So in a sense, they determine all your specifications for any building anywhere. And so these sorts of maps, they only use surface observations. And we showed that the atmospheric reanalysis that I showed you could be used to do building code, not only in the United States, but everywhere. And so now this has become something that the Climate Committee of ASHRAE includes in their quadrannual reports. And so, but I want to emphasize here that they used to just do the last 30 years, but we've also shown by doing this in a rolling way, the types of changes that we're seeing if we just allowed this to change according to the way temperatures, this is based on temperature, basically, temperature and precipitation. And so these building zones, you can see some variability in those building zones. In fact, if we take for the last 35 years, the difference between the last 15 years and the earliest 15 years, you get these ribbons of where there is actually a building climate zone according to assimilation change. And so that's what we're looking forward to, and that's what the Climate Committee wants to do. Now that we're in this idea, we're seeing change, we want to incorporate it. And then 1 minute. Okay. Hey, that's good because I'm almost done. So we don't want to talk about climate change. How does climate change, what impacts may that have? So we have a new project on NASA, and I threw this slide in because I met Doug all last night. But we've been looking at this for NASA centers. This is an example for just Ames. We have downscaled from the latest climate runs. We've looked at 3 of their scenarios, and we have a 22 model ensemble for each. And this is taken from a downscaled data product from a NASA project called NEX. And they have released these data to the public, and we've processed them for Ames. And the idea is there's a low scenario, a mid, and a high, where basically the high is essentially a business as usual. And so the idea is, okay, what's the impact? So on that y-axis is the cooling degree days. And so what you're seeing there is no matter what scenario you have, you're going to increase in cooling degree days, the amount of cooling that you're going to have to provide for these buildings in the future. So we can do this now, not only for the long term, but we can do it by month. And so here's a change on the seasonal cycle of cooling degree day changes. And this is, we've done on other centers, and we see maximum here at the same time of year, this October to September. And then we just did this little arrow diagram. So if you look at the more higher emissions business as usual, we have the different centers here. So we have Glen, which is up there in Ohio, and you can see the reduction. So we have heating degree day reductions and cooling degree day reductions. So you can see the arrows for the different various centers. Even Johnson, which is in Houston, Texas, has an increase of projected increase in cooling degree days. So even though they don't heat much. So the point is, okay, so what's the impact of this? And that's what our project is striving to do. So the last thing to take home is that this sort of exchange of getting data products into people's hands depends on relationships, depends on talking to folks. What information do you need and how can we best provide it? And so we have worked with various different entities from the commercial sector to the public sector to education to try to enable those pathways for people to use the data products. So thank you.
Thank you, Paul. Thank you, Morgan. Thank you, Brad. I think you'd all agree that our three panelists have done a really masterful job providing the historical context as well as the current state of affairs on a number of interrelated topics. So we now have Q&A, and what I'll do is I will kick it off. But in the meantime, please be formulating all those questions. I should also point out that right after this, we have a 30-minute networking coffee break, and all of the panelists will be available for deeper dives. Can you hear me? Jeff, can you hear me at the back? Okay.
I'll take this around for the Q&A.
Oh, thank you very much, Tracy. Okay, so just to kick it off then, and please jump in. So what are the main? Oh, I see. Thank you. So just to kick it off then, what are the main challenges today that prevent us from really harnessing and unleashing the full potential of satellite data?
So maybe I can start that and then you can chime in. So as I was trying to demonstrate that the use of satellite data is very, very strongly coupled to the modeling systems that we're using to then forecast and analyze, as Paul kind of touched home on as well. So to me, what we need to be moving forward towards is a much more complete Earth system modeling framework where we're not just doing weather predictions. We're now, as GMAO is doing aerosol predictions, doing CO2 and carbon monoxide and methane predictions, incorporating all of these different emission inventories into our Earth system modeling, including land component to that. There is land data assimilation systems, but they're kind of decoupled from the broader data assimilation system. So to me, we need to be developing a much broader capability to harness all these different observations, not just the weather observations, into analysis and forecasting.
And I would say on the user side, sometimes it's just knowing that this data is available. A lot of folks who could use this data in decisions they're making right now don't know where the data is, they don't know how to access it. I think we need more platforms like ours that are really helping translate this data into something that can directly be integrated into existing decision processes. Another big challenge associated with that is how can satellite data be used in various decision processes that are already highly formalized. So when we think about evaluating compliance with regulations, when we think about like electric power planning, how can this data fit into a system that already is very complex and has been developed using other kinds of data sources?
Yeah, I think that based upon what Brad Morgan said, I think that you're in it. You have to I think the big word I would say is communication. We really have to let people know what resources are already available. Sometimes it's folks come to us and say, well, I really need that parameter. Like I need, UV. Oh, well, we have estimates of UV down in the archive. And so, those things we can make available, or they need a parameter like backup systems for renewable energy required information about the frequency of clouds in a certain area. And we would just provide the time series. So can we provide statistics that could be used for helping to design battery backup systems? And so the question is a matter of, this is what I need. Can you derive it from what you have? And sometimes the answer is yes, we can do it. And sometimes the answer is, oh, we need more observations. We do need better observations for the air quality and pollutants and aerosols. And we have new satellites going up that are going to address some of those observations. So we can continue to improve and make these available, but communication is the key, getting a good feel for how people are already using the data and if they can replace that with some of these new resources.
All right, any questions from the audience?
I'm ready.
Yes, sir, up on the right there.
I'll bring this to.
Yeah, hi, this is Sheldon Droboff of Ball Aerospace. So great presentation, love that session. I have a slightly philosophical question. I don't know who on the panel wants to take it, but thinking about what we're doing now, what is the one satellite data set thing you would like to have that if we had it, you could say, gosh, if I just had blank, I'd be able to do this or do this better.
So I'll respond to that a little bit. And Morgan kind of did a very nice job at the end of her talk of summarizing what some of the key limitations are. And one of them, the first one was spatial resolution, temporal resolution, long-term record. So I think we'll see in this conference that our current state of the art in terms of, for example, looking for methane leaks on a global scale is vastly better than we had 15 years ago, but still probably not the right temporal resolution. It's polar orbit. I'm talking about Trovomi now. It's polar orbit, it sees once a day, and it's about 4.5 by 7.5 kilometers, so it doesn't see close. So I would say increase spatial sampling, increase temporal sampling. I think the fundamental observing capability is there. We just need to go more higher resolution spatially.
That's a great answer. So I would say specifically thinking about spatial resolution, I do a lot of work on energy justice and environmental justice topics. And there you can get the wrong answer if your spatial resolution is too coarse to your question. And so I think some humility in where we do and don't use satellite data to answer these questions as a spatial resolution is improving. But I think if we had that where we could really look at a more granular level, who is being exposed to air pollution and other harms from our energy system, who has access, that could really open up much more targeted policy responses that could help address historical and ongoing injustices.
Yeah, thanks. I don't think we have an instrument that's missing, but we do require, as I've already said, one of the instruments that has been very eye-opening is the LiDAR and radar instruments to be able to observe the cloud profiles. A lot of this information and imagery is just spatial topography, essentially. You can estimate the various different cloud heights, but you really can't see through the cloud. But when you look at radar and LiDAR for the polar orbiter, you're looking at a 60 kilometer, well, actually a 10 kilometer swath, very small, so, and then you have one shot a day. So those sorts of instruments to improve the frequency I think we have new instruments going up, for instance, a tempo instrument, which is looking at the US, doing hourly pollutant and other information. Could that be done on a more worldwide basis? So I'm trying to, we actually have another instrument. We have some things coming up at the end of the decade with advanced polarimetry to help us with the aerosol properties. So I think there's a lot of advances coming online, and we'll see some things. But this time I can't think of a particular measurement that we're missing, but there's a lot of things in the works. There's a new emphasis on boundary layer processes that I think are very important, particularly, of course, over the oceans when we talk about climate, and but in over land as well. The boundary layer process is basically unobserved. So, but that's a very difficult measurement because you have a lot of scattering interference from the lower layers. So I think there's going to be an emphasis on boundary layer meteorology, and that's one of the things. NASA has a decadal survey that they're working on, and that's going to be one of the things that recommendations that will emerge, and that they're about ready to redo that. So.
Yeah, thinking about it a little more, I do have some instruments that we attempted. So there's a NASA SMAP instrument. I won't go into the acronym, but it's basically active passive microwave measurement, so you can get soil moisture and soil temperature. The passive part has been around for a long time. We use that a lot. The active part failed. So having more instruments so that we can probe, again, thinking about the Earth as a system, the long-term memory over land is in the soil moisture and soil temperature. So if we want to understand short-range climate anomalies and things, we need to have a better constraint on that. So having more measurements like that. And then at the other point, that elaborate on what Paul was saying, with the need for both higher spatial resolution and character and you know these environmental justice kind of issues, we shouldn't discount airborne measurements. So a lot of, you know, in general, there's an airborne equivalent of almost all the satellite instruments, and they provide these, you know, deployable kind of very high resolution kind of imagery like your community uses in terms of the roof mapping, the three-dimensional mapping of roofs and things like that with airborne capabilities too.
I think we have a question over here.
Yeah, Missy Yerard, I'm the director for University Sustainability, and I'm going to ask a question about the confidence level of public and policymakers using the satellite data. And for context, I'm going to call up Dr. Holloway and Dr. Edwards because I came to them with a question. We are building buildings that are going to be around for 100 years. We're using ASHRAE's historical climate modeling for those building specifications. So there are a date before they're even put down on paper. So I asked them to forecast using some of these models out on a decade by decade horizon to repopulate the ASHRAE standards so that our designers and architects can live out. I received a lot of pushback from that. They love the concept. They have a little bit of a question about the legitimacy of science. So as you're building out these historic models and confidence is growing better and better, my jaw dropped when I saw the clarity of some of those satellite images. What is the uptake in public policy to really push some of these future modeling?
I didn't know if that was Tracy wanting to take the answer. I didn't cry in the mic. I mean, I'll make one point on the policy side, which is that a lot of these, so speaking to integrating satellite data with models, these models don't just depend on physical processes, they also depend on social processes. And so one of the biggest uncertainties when we're thinking about projecting building heating and cooling demand in the future is not just what will our climate system do, but what will our human system do? What will our infrastructure system do? And I think sometimes some of the pushback comes from also like very legitimate uncertainty in how much are we going to reduce emissions? Are we going to meet our climate policy targets? And so that has huge implications for, depending on which scenario, you think is most plausible and has huge implications for building heating and cooling demand. So it's both a science and also, or both a physical science and a social.
Yeah, and actually, I think we're gonna have just a rapid fire, 2 more questions because we're pretty much time, but we have 2 and we have a day and a half more. Get questions answered.
In light of time, I'm going to make this short and brief. My name is Elizabeth Joyner from NASA Goddard Space Flight Center. I'm working with Dr. Stackhouse and others across the enterprise to put together something called a data pathfinder for a variety of different end users, focused on the use of renewable energy across the agency. We want to make this particular resource very user-friendly for a variety of different audiences and applications. Anywhere from, I love Dr. Stackhouse's power with the application for GIS users. We know this is something that NASA needs to do a better job in. So I'm interested in practical data users, common questions with renewable energy. What are the issues, the impediments, the pain points? What can little old me do, who's not an expert in energy, do to help design and test and improve upon a data pathfinder to help people find, use, and apply this data. So I look forward to connecting.
So good lead up into the coffee break too. So we have, this is an interesting logistical problem. Sorry.
Tracy, you have another
We
question?
have a question over on the other side. Do you want to start?
I can do one too.
Actually, this is our last question. I'm getting my steps in.
Thank you for your presentation. It's great to hear what's going on. So this is kind of a engineering kind of in the trenches, going out to existing buildings, seeing deficiencies, thinking there's lots of opportunities for improvement. And I think the big one people brought up is predicted weather temperatures to put into models. I think that's a key thing to start with, to get going as fast as possible. And kind of along with the urgency of climate change, here's an outlandish idea. Would it make sense to do more work with, have the professors and the scientists work more with the engineering design leaders, at least the leaders, maybe everybody, or the applied work of designing and creating buildings, and have, given the urgency of climate change, could the professors become designers for a while and at least understand the issues and the log jams in that process?
Okay, well, I think that goes back to the communication aspect, which is really critical. And one of the ways we've done that is by partnering with those who already have decision support tools, and they require input data to those tools. But there's all sorts of people that have these sorts of tools, and your engineering tools, your decision, whenever you make in terms of your decision making process to either evaluate the different technologies that you want to put in a new building, or whether you want to look at improving that building's energy efficiency by adding new technology. Are there tools that you already utilize that could be better informed? Or, some tools like the registry tool or Solar Advisor from NREL, and a number of tools like this, then, and you can connect up those tools and information. So, but I do agree that communication is the key. And in terms of future projections, hopefully within a year, you'll see future projections visually on our website. But that is the issue, is how accurate are they? So one of the things that we do need to do a better job is, so why we've done these ensembles of models, different pathways, is to try to give people a sense of, well, this would be the most extreme change, this would be a least extreme, how does that affect you? There's certain contingencies that engineering can design for. I mean, you can say, okay, well, I'm just going to build in the 10% or 20% extra. You can build that into your design, and then put technologies. Of course, the technology for heating and cooling is changing all the time, which we don't have good access, good understanding for that. But understanding, talking about uncertainty of these predictions is something we need to do.
Great, and this is so exciting to have all this conversation. I'm gonna let Max wrap us up, but I just want to say that we have a half-hour coffee break, And following the coffee break, you'll get to choose whether you want to go to managing risk to energy systems, which is in this room, or energy demand in the built environment, which is in the Northwood room. So hope the conversations can keep going, but that's really the answer to how we can build these bridges. Next.
So I'm sure you all have several more questions. I had some real zingers that I wasn't able to ask because of the time, but I plan to do so in the coffee break. So anyway, without further ado, let's transition to the networking coffee break. But first, let's please thank Brad, Morgan, and Paul for wonderful presentations.